I think we can start and let people trickle in as they go. Just a few things before we actually start with the chapter. So as some of you may remember, Rashans was here last week, and he said if you have any questions about the chapter he was presenting, if you want to contact him about anything at all, that's his Twitter handle, and that's the best way to get in touch with him. He is a chief data scientist at Spoke, and they're hiring, and he wanted to mention it, but it never got mentioned, so I'll mention it now. So if you are interested, or you know people who are interested, they have this machine learning software engineering position, so feel free to apply. If you have any questions about the position, you can probably most definitely write to him directly. Let's see. And then we had a bunch of guys present. Maybe you remember if you were here last time from Standard Cognition. They are a Y Combinator company. And they're doing kind of like what Amazon is doing with this walletless store. Let's see. Oh no. Where is that video? And they were showing us the video that somehow has disappeared. Hold on. Standard Cognition. What is this? How is the thing? Well, that's too bad. Hold on. Am I offline? Okay, there we go. Okay, so that's their video. That's the store, and they're just grabbing stuff off the shelves and walking around, and then they'll be throwing things around, and then they get stuff out of coolers, and somehow their cameras are still able to recognize things. So they were pretty cool and nice, and they too are hiring. So if you'll go to their jobs, I think they have a few positions there. Yeah, so there's that. It's just a 7-person startup. I think the CEO's name is Dave, and it would be Dave at Standard Cognition if you want to write to him directly, see what's what. So there's that. As you know, this is our last meetup for the Deep Learning Book Club. I wanted to say a few things. First of all, it's a pretty good community. If you want to get in touch with people, now that would be a good time to connect with people on LinkedIn or Twitter or whatever. If like you guys come out and hang out with us at the bar, like find me on Facebook or whatnot, I will be reaching out to people too, I'm sure. Also, I'll keep the group alive, at least for a little bit, for a couple of months. So if anybody, like they have a good idea of what would be like a good next book or whatever, or like a good transformation, especially if that person wants to run with it, feel free, let me know, take this over, because there's a pretty good community around this meetup already. And at last, but not at least, all of the videos are on YouTube. So if you want to revisit, if you didn't start with us from the beginning, all of them are there. So there's a bunch of videos that look kind of like this. That's good videos. Those are videos that have been edited, and like they're coherent, and the video quality is good, and like the sound should be good too, in theory. Everything that looks like that, that's like the early days of live stream that we were doing. It's not so great, the quality. It's like 240p. I do have a definite plan to replace them with like a nice high-res videos, because I already have the recordings. So it's just a matter of time of me editing them and making them look more like those guys. And everything that looks like this, so the last 6 or 7 live streams are actually much better quality. So they're watchable as this. They're not painful at all to watch. So you can enjoy them already now. And that is all I have. So we can, work. So we can move on to our presentation now. Let me plug myself.
Well, first, thank you, Elena.
You're welcome, guys. Pleasure all mine. Okay. So I think now we're ready, and I give you our presenter for today, Mimee, and maybe you can tell us about yourself and what you're up to.
So I think on the event page it says I work at Baidu Silicon Valley AI Lab. That was correct. It's no longer correct. I left the job 2 weeks ago, so it's been very exciting. Yeah, so I apologize if you came here because I work at Baidu, but I can still answer questions in case you have some. Yeah, shall we start?
Yeah, we should begin. Don't let me freak you out, but I will turn this around on you. Yep.
We're good, right?
Yeah, we're perfect.
Okay, thank you all for coming here. In preparing for this presentation, I encountered many concepts I didn't understand myself. And how do I put it? I feel like this chapter is really dense. And in the lab, when we have our reading group, these application chapters actually take more than a week for chapters to complete. So they're supposed to be on the slightly dry side. Yeah, this young good fellow here, he's not here. Okay, that's great. I think this chapter just needs a lot more drama. So I'm going to go with this choose your own adventure style. So this adventure is an approximate inference, and hopefully this is sufficient drama to, let me go on. Another thing is that I myself have never been able to have the eyesight to see slides in any conference or talks or lecture halls. So I'm trying to go without. Yeah. But the notes, along with the snarky comments and an unevaluated number of typos, will be posted online, along with a lot of supplementary materials. So that's our first split. We have slides or no slides, and we're choosing no slides. Good. Now let's talk about the book. So specifically this application chapter. There's a lot of math in this chapter. And like I said, I think anything that has math in the presentation needs to be explained and chewed down and have the context offered. So every line of formula should take about 5 minutes. And that's not exactly practical for our chapter in this case. I contemplated how to make this exciting. Maybe I could tell a story or something. But that didn't quite work out because everyone I've tried it on kind of got lost or fell asleep. So I'm going to try to abstract away the math and focus on the intuition behind it. So we actually get something out of it from the learning experience. I hope that is also okay. So another one is math. So math, or just insights. Okay, I'm choosing just the insights. I hope this frames the talk well for you guys. Now this talk will be structured with the notion of inference, why we need to approximate it, some methods of approximating inference. And in the end, I'll talk about why I care about it myself. So inference. Usually / canonically, we have this idea of a trained model versus an inference model. I think this definition, this dichotomy, is largely influenced by industry, where we have development / release. So we think about development as a process of dreaming up the design, writing, editing, or reviewing emerging code, so that we have something fixed where the code is no longer changing, the features are frozen, and then we pack it together and deploy it to users. And that's supposedly stable, usable, reliable. But in our talk, we're not really thinking about that kind of trained versus inference dichotomy. we're talking about inference as something that mirrors the goal for our training, which means that it's a mathematical formulation that we need, so we can look to it and go like, are we doing what we're supposed to be doing? One example I can give is this like crash example. We want to know what the system is doing when we see a crash. Again, this is an industry-inspired example. I hope that's relevant. So we have a crash signal we can observe. Sometimes the application crashes, sometimes it doesn't crash for 5 minutes, crashes again, doesn't crash for 24 hours. So these are the observable variables we can see. And from that, we want to infer what exactly is happening to our system. Suppose we know there are like 100 code paths that the program could be running on to cause this crash, and meanwhile there are maybe a million different things that if the program is running on it, it just shouldn't crash at all. So here we're talking about inference as a way to infer a probability distribution over a set of latent variables, given the observable variables. So in our crashing case, perhaps we will want to know the probability distribution. We will observe a crash signal what is over all the code path that it could possibly have gone through. And here I would like to ask, do I make sense? Yes? Yes? Yeah. Perfect. And now we kind of have a definition of inference, which is the probability of H given V, where V is observable, H is a set of latent variables. Yeah. However, exact inference is freaking hard. There are maybe 3 reasons this is really hard. Sometimes we have intractable inference when we have slightly more complicated relations between our latent variable. It becomes intractable, like impossible to compute, or it gets computationally intensive if we want the closed forms. In addition, sometimes we need more data, otherwise the terms won't drop. So those are the cases where approximate inference is somewhat called for. Just to give you an idea, for instance, I want to know the probability of Mimee, which is me, baking cake. Given that I've got eggs in the fridge, I feel like baking cake, the weather and all these other factors, even something as simple as this quickly gets expensive and intractable to compute. And that is terrible. We can't really let that happen, right? And the solution to that is the ELBO, so the evidence lower bound. The entirety of this chapter kind of falls on the evidence lower bound. For those of you who have read the book, you know that this is the lower bound of the log likelihood of basically our approximation. This is the joint probability of observed data and the model parameters. It is sometimes too hard to compute, as we have said before. And what is really good about this lower bound is that it doesn't cut it up. So that's our ELBO. And I think for people coming from the physics land, they call it variational free energy. Something, yeah. So this lower bound is doesn't restrict Q, which is our kind of like so we have data, we have Q, we have okay. So recall that this one is what we approximate as the probability distribution over the latent variable. We are kind of introducing this new thing into our training process. But instead, what we gain is that, so this is an additional decision we need to make on it, besides the usual parameters we have about the model. So what we get by introducing this new thing is that we now have really, really good computability. In fact, in some cases, this lower bound is tractable to compute where you don't have a closed form. And this lower bound is a strict lower bound, meaning that if we get to maximize it entirely, we know we have exact inference. So this is a proxy through which we do approximate inference. This itself is not an approximation if we're able to maximize it. Make sense? Okay.
Sorry, we have to improvise today with the setup for the blackboard.
Oh,
But it's all good.
yeah, there's not much happening. Yeah. There are 2 derivations about how we get here. And so following them, I'm going to just include them in the resources that I'll post. Okay. And the first one the first method of approximate inference that uses this concept ELBO is expectation maximizing. This is used when you don't have complete data set of observations from X, which is a sample of conditional density. So we go like, what are the chances that we're observing these things, given that there's a bunch of things we haven't seen before? That's the basic underlying idea. Again, this is not quite approximating inference, but rather like with an approximate posterior. And we can think of this algorithm as a coordinate ascent problem. We're kind of trying to bootstrap into the way of more accurate convergence in the end. And it consists of the E step, which is the expectation step, and the M step, which is the maximization step. So this paradigm is one of these things where every iteration consists of a two-step update. This is what you would expect in some kind of dynamic programming regime, where you keep going and one goes about the other. And the special case of this is stochastic gradient descent, where every single step of every M step takes a single gradient. But sometimes this maximization step could be extremely powerful. We could actually get to the closed form. Let's make that more clear. So the other algorithm that kind of follows this paradigm is wake sleep. For those of you who have read the book, this is I'm pulling it from the end of the chapter, which is about learned approximate inference. It's a strange class of methods where the approximation of the inference itself is learned. That is, we optimize for this function mapping from the observed variables to this estimate of the probability distribution. And this is pretty strange, I would say. And naturally, people approximate this with a neural net. The key to this is that we're no longer treating this entire thing as an optimization problem. And what we're doing is to learn a reverse mapping, where we sample from both like the latent set and then the observation set and go like, what could have caused this? Maybe we can learn this kind of relation. And in the end, obviously you learn something, but you end up learning the things that are super probable that you see very often. And from what I read, this method is usually considered not appropriate, or that the effect of it is somewhat weak. But in the book, there are some very tricky explanations about the duration of wake and sleep, how that impacts, and maybe that is why mammals need sleep. So that's maybe the drama of this chapter. And the next one is variational inference. So far, we have seen our optimization gets broken down into these two steps, whereas Ian puts it in the book. So the learning step is we're maximizing this proxy ELBO L with respect to theta, which is our set of parameters, whereas the inference stage, we're maximizing L with respect to Q. So Q is the thing where we get to choose. But variational learning is about choosing this family distribution that is easy to compute the log likelihood of. What follows from there in the book is not exactly easy to follow, I would say. And while I can go through the math, I don't think I get much insight from it, unfortunately. I think I just personally don't have enough contextual information to make that memorable and good. So instead of following it, I think I'm going to supply people with a lot of supplementary material. And if someone else has more insights or context or things to present, you're welcome to. But here I'm going to talk about the cool bits I get from this derivation. One includes imposing a strong assumption that Q here is a factorial distribution. So that's called the mean field approach. And then we can just add a probabilistic graphic model to it, and then we get structured variational inference. This is super cool because now we don't need to parameterize Q ourselves. We're not really making that kind of really explicit choice when we do these things. In terms of computation, we don't use gradient descent to compute the mean field, but instead we use a fixed point equation to do updates. And I thought that was pretty cool as well. I know there's a bunch of math in this, and if you read the book, you've seen it's rather ugly. The TLDR from this is that with some loose assumptions, the ELBO can be like this. This term could be expressed as a series of steps that are pretty easy to compute arithmetically. Right, so we did all this really ugly work, and we end up with things that are actually computable. So that's a huge gain for us in that sense. Again, I'm hand-waving all the details because they're hard to present without strong contextual information. I hope those interested in it can share more with us how to intuitively understand these concepts. Okay. Now we switch gears and talk about the effect of using approximate inference. Let's revisit this before. We didn't have the Q term before in our training process, in our optimization, and we introduced it in this ELBO approach. But what we gain is computability, but what have we lost? So here, because it's usually a two-step approach to do like for data with a set of parameters, we're also kind of choosing Q in the process, step by step. And what ends up happening, as you would expect, it's kind of like, some people call it chicken and egg. I'm not sure if that's a good analogy, but whatever you assume to be the family of distributions on Q ends up being true as you train it, because you assume it's true, and then you find the parameters, and then you maybe do a little bit of jump, but it doesn't quite leave your assumptions about this family of distributions. Whether or not this is optimal or even close to true is up for debate. And the way people do it is a lot of like testing techniques. You could call it model testing. They might be able to estimate the term that we said is really, really difficult to compute, and they go like, oh, my gap in the very end after training, this is actual value is super small. So I think I'm like pretty much there, right? So those are some testing techniques that I can also include in the supplementary material. There's also a Bayesian inference workshop every year at NIPS, for those of you going to NIPS. And if you have good ideas, I think the call for paper is still open. And the last one we're going to talk about is the math inference / sparse encoding. You could say variational inference is an extension of this one. So we are computing the single most likely value of the missing variables, rather than inferring the entire distribution. This is also not exactly approximating inference, but since we're only using one, and the way people are using it is to approximate the rest of it, this is in this chapter. Yeah, so it's approximately approximating. So the way people do it is to use a, I think it's called direct. It's basically the delta function in physics. This is basically used to drop terms. It doesn't quite have any practical meaning as far as my perspective goes. People are using it just so that we have only one result left in this entire process. Sketchy as it sounds, or I think it's sketchy, math inference is really popular and is commonly used to extract features. It's frequently combined with sparsity assumptions, like the sparse encoding models where you impose sparsity on the inducing prior. This does have the drawback though of overfitting with high dimensions. When we have a lot of high dimensions, we end up overfitting to the thing. So our trained model will end up have pretty high generalization error. Okay, I hope people have been following this.
Is everybody following? Can you guys hear in the back? That's the biggest one. Okay, cool.
Okay, so far the talk has been about using approximate inference. As a problem, we would want the inference to help us in training. And this is ironically not the reason I am interested in it. The approximation techniques used to derive inference can let us dive deeper into the influence or the effect of the data on the trained results. Ideally, I want to know what the data would do to the model if we haven't seen the data at all, or what the data had done to the model, suppose it's in our training set, without this old or new data through the model. So in the case of old data, what you would do is to take that data out and do a retraining, right? In the case of new data, you're putting new data through the model and running it again. I want to not do that, but still know the effect of this data on the model. And because of all these optimization methods that have been proven, and people have known that that there are reasonable bounds that we can draw from it. This is super useful because then for any choice of optimization, I have reasonable bounds on how close they are to the exact one, and we don't have to compute this by hand. And then you can take the ELBO and infer what the parameters, so that's the theta, tell us about the influence of the model at every single step of the optimization. Which means I feed it data, some changes happen to theta, and I wonder what those changes are. So that's what I'm interested in. I'm kind of still working on making the math work myself. So if you have insights into that, feel free to come to me. I also have a workshop poster at MIPS. Yeah, that's coming up. But that has more of like a security focus. You're welcome to talk to me about that as well. So because we've chosen those slides, just to summarize, because we've chosen those slides, there will be notes and supplementary materials posted. And here we've chosen insights over math. We can work through some of the math amongst us after this talk. But this concludes the presentation of this chapter.
Okay.
And this is short.
Short and sweet questions before we move on. That was super fast and very cool.
I'm pretty open to going through the math.
Is there interest in going through some math?
We can do it off the video.
Off the camera? Yeah, we can definitely workshop it. No? Yes? Questions for the chapter? Questions about Baidu AI Labs? That are not like non-disclosure things? No? All right.
Okay.
Well, thank you.
A little time to like absorb what just happened.
All right. Well, first of all, thank you so much.
Yeah, people say I have the habit of like overflowing other people's stack. It feels like a serious allegation. And if you have feedback on the presentation, please let me know. I would like to be a better speaker myself too. Thank you.
Thank you. Well, okay. I guess this leaves us for more time for beers. We probably will not go to town hall because it's been difficult. So we'll go to Palermo, which is a block away. Mimee, will you be able to join us for a drink? Or
My birthday.
and then when people will warm up maybe for more questions?
Okay. I might not have my ID. But
I think
it'll be okay.
you'll be okay.
Okay.
Yeah.